everybody. Today we're talking about the ratio test, one of the most powerful tools at our disposal for testing the convergence and divergence of infinite series. Suppose we have some infinite series, sum n equals 1 to infinity, a sub n. It could start at a different n value, that part doesn't really matter. The idea is to look at the ratio of adjacent terms, an plus 1 over an. Take the absolute value, and then consider what happens as n gets large. Limit as n goes to infinity. If that settles down to a number less than 1, call it L, then the series converges absolutely, and therefore converges. If the limit is L greater than 1, or if the limit doesn't exist, then the series diverges. If the limit L is exactly 1, then the ratio test doesn't tell us anything. We need a different technique to determine if the series converges or diverges. So let's do a few examples. Let's start with the sum n equals 1 to infinity, negative 1 to the n minus 1, n squared over e to the negative n. Applying the ratio test, we look at the ratio an plus 1 over an. So that means plug in n plus 1 into that formula, an, and then just copy down the formula in the denominator, an plus 1 over an. Take the absolute value, and then take the limit. Now, of course, the absolute value is going to kill all those powers of negative 1. Also, we're going to immediately get a simplification with the e to the negative n minus 1 over e to the negative n. We're left with a single factor of e in the denominator. This is an infinity over infinity form, so let's use L'Hopital's rule, differentiate the top and differentiate the bottom. Do it again. Overall, we get 1 over e. That's less than 1. Therefore, the original series converges absolutely by the ratio test and therefore converges. Example 2. Sum k equals 0 to infinity, k factorial over 3 to the k. This time we don't have to bother with the absolute values because the terms of the series are all positive. So as I do the limit as k goes to infinity, a sub k plus 1 over a sub k, I get k plus 1 factorial over 3 to the k plus 1, that's plugging k plus 1 into my formula, over k factorial over 3 to the k, just using my formula. Rewriting that slightly, I see a lot of simplification. On the right, 3 to the k over 3 to the k plus 1 is just going to be equal to 1/3. All the other 3's cancel. On the left, I have to remember that k plus 1 factorial is the product of the first k plus 1 integers. And of course, k factorial is the product of the first k integers. So everything cancels there except for a single factor of k plus 1. Overall, limit k to infinity, k plus 1 over 3, which is just infinity. Therefore, the original series diverges by the ratio test. One more example. Let's see a case where the ratio test is inconclusive. This is the alternating harmonic series. K equals 1 to infinity, negative 1 to the k plus 1 times 1 over k. And we already know that it converges conditionally. But let's use the ratio test on it anyway. Let's look at limit k goes to infinity, absolute value, ak plus 1 over ak. Of course, the absolute value sign is going to kill all of the negative 1's. So I'm just left with 1 over k plus 1 over 1 over k. Taking out the absolute value signs because I don't need them, and then multiplying by the reciprocal of 1 over k, I get the limit k to infinity, k over k plus 1. And that's going to equal 1, for example, by L'Hopital's rule. Therefore, the ratio test is going to be inconclusive here. And we need a different technique to show that the series converges. For example, the alternating series test will do it here.